Okay, this is going to be lesson number 9 in chaos, fractals, and dynamics. Last time we defined what the Mandelbrot set was, defining it in terms of the complex numbers. We said we were going to continue iterating on the function f of x equals x squared plus c, but we were going to change the name of x, call it z, because we want to be reminded that we now have a function that can have complex elements in both the domain and the range. And so z, so the traditional symbol for complex number. We're still going to use a seed of 0, and c, the value of c can be any complex number now, not just the real numbers. If we iterate on a certain value c, starting with a seed of 0, and we get divergence. Any value of c that does not lead to divergence is going to be in the Mandelbrot set. Anyone that does diverge will not be in the Mandelbrot set. So if it stays close, if it doesn't go off to infinity, it's in. We're going to make an assumption that when the iterated value gets more than 2 units from the origin, the orbit has escaped, because once it gets that far away, it's bound to escape. Also, if you want to find out how far it is from the origin, because z has a real and imaginary component, you simply have to use the distance formula to find that distance. And along the way, sometimes we'll be counting the number of iterations taken until it escapes, until it gets more than 2 units from the origin, until the orbit gets more than 2 units from the origin. Let's take a look at what we had last time. You may recall that last time we had gone from what we had been developing over the first bunch of lessons, the real numbers of the Mandelbrot set, and we had iterated on a couple of other numbers, actually 3 other numbers. One was -2 plus 0.1i, and that did not escape. That homed in on a particular value. It was an eventual convergence. And we also tried I, and found that that went to an immediate 2 cycle. Then we tried a number over here. I think it was 0.2 plus 0.6i. And that diverged, went off to infinity. So those are 3 numbers that are not pure real numbers that we tried. And we found different behavior in each one. But what was important was these 2 were in the Mandelbrot set, and this one was not. And what we want to do is check all of these other numbers. We want to do it in an efficient manner so that we don't take forever. So we're going to try to come up with a decent way to do that. And let's look at the following. Okay, there's a lot going on here, so let me take a little time to explain it as best I can. Here is our initial value for c. We call it point P. And like this initial value is going to be -1.242 plus 0.004i. So the real part, the imaginary part is how we're doing this. Up here is the number of iterations we're going to take, always using a seed of 0. And we're going to graph those iterations. And but we don't always want to graph all of them, because as you know, it sometimes takes some time for them to settle down. So this h here is going to be the smallest number of the iterations we're going to graph. So if I wanted to start with the 10th, I just make h equal 10 and ignore graphing the first 9, so we'd be able to see the pattern down the road. Okay, so here we go. I want to grab that point, move it somewhere. Well, let's just leave it. That's about a -1.3 with a little imaginary part. We'll ignore that. That's no big deal. And I'm going to iterate. And I want you to watch the red dot. Notice it jumps over there, jumps back, jumps over there, jumps back. And it is jumping among, I think you'll eventually see, it's jumping among 4 different numbers. And we knew -1.3, I believe, is a 4 cycle. Anyway, it's definitely, one thing's definitely happening. It's not escaping. Okay? And we'll know it's escaped because the distance here will become greater than 2. And we're going to go up to 100 iterations, and it does not escape in 100 iterations, so we're going to assume that it never escapes. That's not always a good assumption. There might be something that hangs around for thousands of iterations, and we think it's in the Mandelbrot set, and eventually it escapes. And that will be important in determining what are we really seeing when we say we're seeing the Mandelbrot set, but we'll deal with that later. You'll notice that if I want to, I can eliminate the first, let's just eliminate the first 50 iterations. And so if I wanted to graph to see the last few, I would just have those, and I wouldn't have all the extra ones. Now, what I want to do is move my point off here. Now I'm going to do, let's do 40 iterations, and let's see all of them. And as I move my point, you'll see this guy has not escaped in 40 iterations. There's all sorts of points in the iterations, but you see what happens at this point here, for instance, eventually homes in and becomes a single point. In other words, it's a eventual one cycle. As I move around here, now look at that. That guy's escaping because the distance got really big as I up the iterations. If I move over to here, it looks like that's eventually homing in on a particular number too. Jumps around a lot, but you can see it's homing in on what appears to be one and only one number. This will eliminate a bunch of the iterations, and you can see it is in fact gradually going to a one cycle. Now let's look at some other points through this point here. We're going to gradually increase iterations, and we're going to show all of them at first, and we're going to see what happens. You can see almost right away this settles down into a 3 cycle. So this value of C, negative 0.127 plus 0.714i, looks like it's an eventual 3 cycle, which means it is in the Mandelbrot set. Let's look at one that escapes. Notice that the point we're considering, the value of C, we're considering, I call P for point, probably should have called it C. And it's listed up here, the real part and the imaginary part. And so that's what I'm considering. There's a point right there. Let's let n gradually increase. You can see up at the top the values of the iterations and the distance they are from the origin. And this looks like it's kind of bouncing around, maybe becoming a cyclic performer. But as you can see, it bounces up, it bounces down, and each time it's further and further away. And at this point, the distance is 2.229, which means it's never going to come back. Escape is true. So that point would not be in the Mandelbrot set. You can see there the distance has really gotten big. Okay, so what we want to do is go all over the place and find out what points are in the set and which ones are not, and mark them. And we also want to find out how fast the points that are not in the set escape. And this is not the best situation to do it in, although I can see some things happening. I've got 37 iterations. You can see there's something that escapes as I move around. There's something that homes in on one point. That looks like something that maybe homes in on 1, 2, 3, 4, 5 points. So that's probably a 5 cycle. All these guys up here escape. And that guy, goodness knows what he's doing. Looks like he's a multiple cycle though, doesn't it? And he certainly does not appear to be escaping. Well, you never can tell with just a few iterations, but it looks like it's not escaping. Well, I want to get the whole big picture. And to do that, I'm going to look at another piece of software. This is a little program written in Visual Basic, and there you have your real number axis, your imaginary number axis. Up here it tells me where my pointer is located at, and so I want to do pretty much the same thing I just did, and then we're going to go a little further. So we'll notice if I go here and I click on a point, say there, it quickly goes off the screen, and it took only 3 iterations for it to escape. And so this point is not in the Mandelbrot set. The ones out here, in general, you're going to find them escaping in very few iterations, 2 iterations there. In here, sometimes it's real close to points that don't escape, but they do. This one escaped in 33 iterations. Notice I'm going to 1,000 iterations now, so I can identify some points that are not in the set that take a long time to escape. The red point was the point that I was testing, and these are all the iterations. Of course, if I go in around here, I get 1,000 iterations, which indicates that it's in the Mandelbrot set because it never escaped. We're assuming that 1,000 is enough, although it might not be. That one took 4 iterations, 20 iterations, 1,000, 5, 8, 5 again, 13. And you can see there are all sorts of possibilities here. 14, look at that. It took 510 iterations for it to escape. That's one that we would have thought with the other software was in the set, but it actually isn't because it eventually escapes. Okay, well, let's look at another similar program. Now this little program here essentially does the same thing as the other one we saw, and also pretty much the same thing as the GeoGebra thing did, except as follows. I've got a grid here, and if I click on the grid, say right there, it tells me how many iterations it took for that point to escape. See right there? It took 4 iterations for that point to escape. But it also colors the square that that point is located in. In this case, it colors it white because that's not in the Mandelbrot set. Now, what we're doing there is assuming that every point in that square has the same behavior. In other words, it's either every point in the square is in the Mandelbrot set or it's not in the Mandelbrot set. So that way we can get a picture of the whole thing when we're all finished. So I'll come down here, for instance, click right there. Notice that that square fills in with blue. It took 30 iterations. Well, 30 iterations is the maximum number of iterations I'm taking. If it lasts more than 30, I'm just assuming it's in the set, which means I'm going to have more points in the set than are really in there. But that's always going to be the case because you can never take an infinite number of iterations. This should give me a pretty decent picture of it. So I come here, click there. There. All those points that I clicked on are in the set. Click out here. That baby escaped in 2 iterations. You see there? Click here, here, 3 iterations, 9 iterations, 19 iterations, 30 iterations, which means it's in, as far as we're concerned. That one got out in 10 iterations, 6 iterations, 24 iterations, and so on. So what I'm going to do is just hold down my mouse button and check a whole bunch of points. Remember now, this is the complex number plane. We're going from -2 to 2 real and -2 to 2 imaginary. And we're checking these points to see if they're in the Mandelbrot set. And if they are, we color the squares for that point one color. Now that means if I click twice in a square, I might get 2 different results because there might be some points in there and some points out of the Mandelbrot set. What I'm doing, instead of clicking, I'm holding down my mouse, which enables me to go faster covering points. And a kind of interesting thing happens, and this is probably what Benoit Mandelbrot first saw when he saw a graph of the Mandelbrot set on a paper printout. Very crude drawing that kind of looks like a bug. And let's just fill in the whole thing now. And there it is. Okay, if I checked every point in there, that's what I would get. Of course, it's not a very smooth picture because I'm filling in squares instead of graphing points or pixels. Okay, so that's the general shape of the Mandelbrot set. It's a little bit of a surprise because I think we would have expected that there would be some nice, maybe a circle of points with everything outside the circle not being in, everything inside the circle being in, maybe some nice simple shape. This looks a little strange, really. Okay, another thing I want to look at, you remember I said it was going to be kind of important how many iterations it took? What I want to do here is instead of black and white, I want to go with color. And you see this guy here, he took 14 iterations. He gets a white color. That guy took 12, he gets a pink color. So the blue ones are in the Mandelbrot set. The others are identified by how long it took for them to escape, how many iterations. And I'm just going to fill in that whole thing. And you get a kind of a nice pattern in that outside, these guys are all the ones that took 1 to escape. These took 2. These took 3. These took 4. When you get down in here, something interesting happens. It gets complicated. That took 11 iterations. That took 7. That guy took 6. 9. When you get close to the boundary of the Mandelbrot set, it's not so easy to predict how many iterations it will take to escape. A point that doesn't take very many iterations to escape might be very, very close to a point that takes many, many iterations to escape. So it's not, on the outside you have this predictable pattern. At the boundary, it's not so predictable. We're going to want to investigate that in more detail in the next lesson. And I think that'll do it for this lesson.